Today, actually, we will be talking on oxidation due to other gases. Here, actually, the atmospheric gases which are available are mainly carbon dioxide, sulfur dioxide, hydrogen sulfide, halogen, mainly chlorine and fluorine. I want to mean actually, there are so many atmospheric gases are there in the environment. These are the gases which are responsible for oxidation due to other gases. Actually, what will be the intensity of corrosion due to this will depend on two factors. Number one, chemical affinity of the metal and the gas involved, and devastating action, how much it will be decided by the nature of the film being produced on the metallic surface. One thing I would like to tell you very clearly, in case of oxidation due to oxygen, the layer being produced on the metallic surface was termed as oxide layer, but here we will never tell it oxide layer because oxygen will not be involved, and therefore the name of the layer will be turned on the basis of the actually the gas involved in this process. Such as if chlorine is involved, the name of the layer will be chloride layer, like this. Now, actually, what do we actually like to tell here? Based on the nature of the film being produced due to oxidation due to other gases, are classified into three categories. Number one will be stable or protective. If the layer being produced is protective. Number two will be volatile, and number three will be porous, depending on the nature of the film being produced. Let us start with first one, if the layer being produced is stable or protective. Say the layer is stable. What does it mean? Let us take a metallic structure made of silver, and the structure is kept in an environment where chlorine is there. Automatically it will be attacked by chlorine. What will happen? Silver plus chlorine will produce here silver chloride, like this. This is your silver chloride. Now, the particle size of silver chloride is extremely very small, as it was in the case of aluminum oxide, Al2O3. That we have seen earlier. If the particle size is very small, it is going to make an uniform layer on the metallic surface, as a result of which number of holes and pores or cracks will be less, rate of corrosion will go down, and ultimately it will be stopped. What does it mean? It is now very much clear. If the layer is stable, that is protective, it means the particle size will be very small. It will make uniform layer and adhere tightly on the surface of the metal. Number of holes and pores will become less, rate of corrosion will go down, and ultimately it will be stopped. This is the best example. Layer of silver chloride on silver. This is all about your first one. Now let us see second one. Volatile. If the layer is volatile. In case of volatile oxide, we have seen earlier. All of you know that what is volatile. Let us take a metallic structure made of tin, SN. Now, if this structure is placed in an uncontrolled area where excess amount of chlorine is there. We know that if tin is allowed for chlorination in a controlled condition, it will produce SnCl2. But if condition is not controlled, it will be further oxidized to SnCl4. That is why I have used the term uncontrolled. So in this situation, what will happen? Sn plus Cl2 ultimately will produce CN4, SnCl4. This is your SnCl4. As in the case of volatile oxide, we have seen earlier, if the oxide is volatile, it will go up. Similarly, SnCl4 being volatile in nature, it will go off as soon as it is being formed. As a result, the entire metallic structure will be exposed for further attack. And therefore, it will go on like that. It will go on. It will be produced and go off. And this process of corrosion will be continued till the entire metallic structure is not being destroyed. The best example is layer of SnCl4 on Sn. This is all about your, if the layer is volatile in nature. Now we will be talking about last one, if the layer is porous. This is very, very important, and we have to see it very, very carefully. And this is particularly important in petroleum industry, where mainly because of hydrogen sulfide. We know that hydrogen sulfide is naturally present in crude oil. And we know that crude oil is refined through different processing in refinery, in petroleum industry. And hydrogen sulfide may also be produced during refining of crude oil, like hydrocracking, hydrolysis. We all know that. It is also known to us in petroleum industry, we generally use mild steel for infrastructural purpose. As all of us know it, that is, mild steel is low cost, it has good mechanical properties, and it is extremely resistant towards corrosion due to the actually inclusion of a specific organic compound, dimethylamine benzylamine or its derivative. Because of this compound, mild steel attains some kind of special protection towards corrosion. Because of that, mild steel is extensively used in petroleum industry. Now, the problem is that when this mild steel comes in contact with hydrogen sulfide, it is very, very dangerous. You know that hydrogen sulfide reacts through electrochemical mechanism. And during dissociation of hydrogen sulfide, the product being produced is also very, very devastating. They catalyzes the electrochemical reaction. Let us see how does it happen. As we know that this is your mild steel. It is being attacked by hydrogen sulfide. What will happen? Initially, Fe plus S minus plus H plus. Actually, the mechanism how hydrogen sulfide attacks iron is not very much clear. It is poorly studied. But we have two proposed mechanisms. We will be discussing here both the mechanism. Once this is formed, they will proceed by two different mechanisms. Let us see one by one. Fe plus H2S, it will be producing Fe plus HS plus H plus, like this. There are two mechanisms. By this mechanism, it will be producing Fe HS minus plus H plus. Then it will be producing like Fe HS plus plus H plus E. Try to understand that. Initially it was -1. So 1 electron is lost, this one. Now when it becomes plus, so automatically this electron is being actually taken by H plus to produce H. And ultimately it will be converted into FeS plus 2H. Similarly here, this thing can again be converted like that through this mechanism, Fe plus S minus H plus. This thing will now be converted into S2 minus plus 2S plus. Now Fe2 plus S2 minus plus 2H. This will be your ferrous sulfate plus 2H. Now this thing actually will follow Taylor pairing. In Taylor pairing, what happens? I am showing 2N FeS, it will be converted into N Fe2 S2 and ultimately FeS. These are two probable mechanisms. Although the validity of the mechanism are not very much clear, but we generally believe this is the pathways through which hydrogen sulfide attack your milestone, as a result of which it will cause serious damage to your petrochemical industry. So this is how other gases may cause serious kind of oxidation type of reaction. This is all about your oxidation due to other gases. To summarize, I would like to tell you, we have seen there are three kind of layer may be produced due to oxidation due to other gases. Number one is oxidation, if the layer is stable in nature, as in the case of silver chloride. And second one was if it is volatile, as in the case of SnCl4. And third one is if it is actually in petroleum industry, if it is attacked by hydrogen sulfide, which is either available in crude oil naturally, or it may be the product of hydrolysis during refining of crude oil. Once the infrastructure made of mild steel in petroleum industry get affected by hydrogen sulfide, the intensity of damage will be extensive. We have to be very, very careful about attack of hydrogen sulfide towards mild steel. This is all about today. In the next lecture, we will be talking on liquid metal corrosion. I hope you might have understood everything. Please go through the video very carefully. If there is any doubt, note it down, make your presentation, and we will actually discussing and clearing all doubts in the next lecture. Thank you very much.